along with the slides will be posted to our EERE website in about 10 days. We will send out an email to attendees once those are posted to the site. Next slide, please. All attendees will be on mute throughout the webinar, so please submit your questions via the question box that you should see on your webinar panel. We will cover those questions during the Q&A at the end of the presentation. Next slide, please. With that, I would like to introduce our DOE host, Dimitrios Papageorgopoulos, joining us from the Department of Energy headquarters in Washington, D.C. Dimitrios is the Fuel Cell Program Manager in the Fuel Cell Technologies Office. It's a pleasure to have you, Dimitrios. Good afternoon.
Thank you, Chris, and thanks to everyone, and good afternoon. It is my pleasure to introduce Dr. Vojislav Stamenkovic from Argonne National Laboratory, who is today's presenter. Voya, as he's known, is a staff scientist, technical leader, and principal investigator at the U.S. Department of Energy's Argonne National Laboratory. He earned his PhD degree in physical chemistry from the University of Belgrade in 2001 after spending 3 years as a visiting scientist at the University of California at Berkeley. He was a postdoctoral and staff scientist at the Material Science Division of the Lawrence Berkeley National Laboratory before he moved to Argonne in 2006, where he's conducting multidisciplinary research related to materials for electrochemical applications, such as fuel cells, electrolyzers, and batteries. Dr. Stamenkovic received a number of awards for his work, such as Recognition Award from Lawrence Berkeley National Laboratory, Distinguished Performance Award from the University of Chicago, and our own US DOE Hydrogen and Fuel Cells Award in recognition for his contributions in catalyst research and development. He has published over 130 articles and book chapters for which he received over 17,000 citations with an H index of 55. So, with no further ado, Voya, take it away.
Dimitrios, thank you very much for introduction. And I'm really happy that I can share with the broader audience actually what is going on in fuel cells. And certainly thank you, Chris, for organizing all of this. It's a real pleasure to actually broadcast in such a way which is still new for all of us. And I think it's really advantageous that actually not only people who are local, but people who are certainly international can reach out and have detailed insight what is going on. For that reason, today I will not be focused entirely on what is going on in our group, but it's more the main purpose of presentation is actually to bring awareness about past, about what is going currently, and about future challenges in our field. And having said that, the main emphasis is going to be on what has been achieved and how much of great progress has been made over the last several decades. So to start all of that, you see that introductory slide with all of those fancy nanoparticles. I hope that I will have some time to go into details, but before we reach materials that are exotic in some way, I would like to show you and start with slide which is our current state of the art, and this is fact that right now we do have real fuel cell car on streets, and this is Toyota Mirai. So thanks to actually enormous effort which was going on globally for a number of decades, engineers were able to achieve something which is absolutely state of the art. Moreover, it is also important to say that this car is using and relying on platinum-based materials. And having said that, to be even more specific, there is pure platinum anode and platinum alloy, like platinum cobalt on cathode of this fuel cell stack. So how all of that started? So many years ago, actually, fuel cells were really in I would say infant phase of applications, and back then actually I would say global attention on fuel cells was coming from the fact that they were applied in space applications. So first Gemini program was using, believe it or not, a PEM fuel cell with unsupported platinum catalyst with extremely high loading. So you can see here that we are looking to loadings that are probably like 200 times higher than what we have right now. Apollo program switched to alkaline fuel cells, so temperature was around 250. And going into something which was more recent, like Space Shuttle program, again, they continued with alkaline fuel cells, and they were relying on platinum alloy catalyst, still with extremely high loadings. Back then, durability was not enormous focus except to reach target for the mission they were looking at, and in most of the cases, those were actually time frames between 1 week and 2 weeks max. So going from something which is high-end application into early onset of approach that we sometimes like to term as fundamental science. So I like to use this slide because this is one of the first papers that came out from Nenad, Hubert, and Phil, which was reflecting structural sensitivity of platinum single crystals for the most challenging reaction in fuel cells, and this is cathodic oxygen reduction reaction. So from those high-end applications into single crystals, and it's a long way, but certainly this is the only approach which can tell us actually what should be done and to which direction our focus and research should be placed in order to reveal the real structure function properties of catalysts that are usually employed in real devices. So here what you have is typical platinum carbon catalyst supported in high surface area carbon, and if we are careful enough and if we are using highly sensitive equipment, so we can even distinguish that those nanoparticles are highly crystalline, and they do come with certain facets, and they can be any of those like base single crystalline orientations, and for that reason, if we are aware that structural sensitivity exists, as it was shown on previous slide, then it is no big surprise to claim particle size effect, and for that reason this is, I would say, the first parameter that one should be aware in any kind of catalyst design. So going from something which is very challenging demand, how to design catalysts that are going to meet our technical targets. We have to be aware actually of limitations, and usually they're expressed, at least in our case, as well-known DOE targets that are, I would say, they're revised every 3 to 5 years. And right now we are looking into 2020 DOE technical targets where mass activity of catalyst at 0.9 volts for cathode is 0.44, and also it is very well defined what electrochemical area loss should be, so the most desirable would be below 40%. And also PGM total content, total loading, which is probably one of the main targets, which is directly related to the total cost of fuel cell stack. So in short, I would say the main challenges are activity, durability, and platinum loading. So we are looking into those, and actually my presentation today is going to be focused entirely on ability to address each three of them. So, and I will try to use, as I introduced in the beginning, this fundamental approach is something which is the only way how we can advance in the field, not only to address and to learn about structure function properties, but also how to utilize them in order to achieve advanced catalysts, and that means catalysts that are extremely active but at the same time durable. So, and again, I'm not addressing only activity but durability as well, and as you are aware, in many of those reports we can find that catalysts are not stable and to which extent everything degrades. But there are only a few studies that are actually useful to, and they were capable to point out what can be done in order to increase durability at fundamental levels, so by actually tuning fundamental properties of catalysts. So several options we have that are coming not only from our labs but across the entire field, and particular attention is going to be placed on so-called structure function properties, where certain type of geometric surface structure is playing critical role in determining activity but stability as well. And then what we can do to increase that, and how alloying is going to affect overall performance of the catalyst, and in addition what can be done with targeted surface modification and again intentional tailoring of catalyst properties. But also one should keep in mind that talking about advanced catalyst or materials, it's not only solid side of if you like, fuel cell electrodes. So we have to be aware actually, and we need to consider the entire interface, which is very complex, and I will get to that point. Probably this is going to be the last portion of my talk today. So I will begin with platinum single crystals and the fact what I already presented in one of the first slides. So here you can see a snapshot of basically the three base planes of platinum single crystals, and the fact that the activity range for oxygen reduction reaction can vary between the most and the least active catalyst for a factor of 3. So this is extremely important for any future claims that one is going to make about improving catalytic activity. So before we make any claim, we have to be certain that this is not coming from just simple morphology modification of the surface that one can certainly do. So the most active surface is 110 and the least active surface is 100 in case of non-absorbing electrolytes such as perchloric acid. Situation is quite different in strongly absorbing electrolytes, and so this is a slide which reflects activity, and what is going on with stability is something which was just recently revealed from our group again. And what we did is actually we managed to couple two methods. This is rotating disk electrode with inductively coupled plasma source, which ends with quadrupole mass detector. So that gave us extremely high sensitivity to detect dissolved metals from single potential cycles, and basically our detection limit was in the range of ppt. So to be accurate, this is part per trillion, so extremely low sensitivity. And basically what you can see in lower portion of the slide, those are basically results from single potential cycles obtained from different single crystals of platinum. So here is actually quantified result from single crystals, and you can see that actually the least amount of dissolved platinum is coming from platinum 111, which is in some way not surprising because this is very close, densely packed surface. So in other words, those surface atoms, they have the highest coordination number among them, opposed to platinum 110, which is the least stable, and for that reason that surface has the highest amount of dissolved platinum. So, and if we express that in factor, this is like substantial difference between those two. So why all of that is important? Well, if you take a look what is going on with platinum carbon catalyst, which was treated in the same way as I explained here, so it is well known that we can use platinum carbon catalyst, deposit on rotating disk electrode, and then we can observe actually the amount of dissolved platinum. So this is really substantial, and it goes even beyond the most unstable surface such as 110, which is in some way not surprising considering small particles. In fact, they are very rich in edges and corners. In other words, surface sites with the extremely low coordination number. And those atoms are the most sensitive for dissolution. So now I will switch gears into something which is related to what we can do, and the first question is actually what we can do to improve activity. So, and alloying is something which is well known. So those are results that are coming also from our group. I would say that was early 2000. And I was looking into platinum, cobalt, and platinum nickel alloys in vacuum first. So extended, well-defined surfaces. Later we switched to single crystalline surfaces, but the point and message here is actually, so in order to obtain clean surface in vacuum, one needs to apply so-called sputtering in order to get rid of any impurities, and this is how morphology of sputtered surface looks like. However, after annealing, that surface is getting very smooth with nicely ordered atomic structures in case of single crystals. But what was also interesting that surface composition of those annealed alloy surfaces turned out to be pure platinum, and we, even after awareness of doing all of those experiments in vacuum, we termed that surface platinum skin. So in addition to distinct surface structure, which is confirmed from lead studies, we could assign actually that surface composition was pure platinum. And what was extremely appealing is the fact that we were extremely eager actually to learn how all of those surfaces with very same surface composition as pure platinum single crystals, however different bulk composition, how they behave. And here you can see comparison between pure platinum and platinum nickel single crystals. So, and when you do those kind of comparisons, I mean, you're looking into three curves, it's very difficult to see one-on-one. So, but what is message from this slide is fact that actually there was an artifact that platinum 111 skin was for one order of magnitude more active than any of those like pure platinum surfaces. And if we express that towards state-of-the-art platinum carbon catalyst, we are looking for the factor of improvement which is almost 2 orders of magnitudes. So that's the reason why I'm bringing only this platinum 111 skin versus corresponding platinum 111 single crystal, and difference between those geometrically the same surfaces with exactly the same arrangement of platinum surface atoms. However, different bulk composition is tremendous if you compare just cyclical thermograms, and we can see suppression of hydrogen UPD by a factor of 2. Not only that hydrogen UPD was suppressed, but also the onset of surface oxides is shifted for over 100 millivolts. And all of that is followed by a substantial boost in catalytic activity which was observed. So in essence, we were looking into those two cases, one with pure platinum, which was significantly covered with so-called oxygenated species that are coming from water at potentials that are relevant for oxygen reduction reaction, and case where we have again pure platinum surface, however subsurface was nickel, and that nickel was influencing topmost platinum atoms in such a way that electronic modification of topmost platinum atoms is substantially changed and altered, leading to substantially lower coverage of those oxygenated species, which leaves substantial amount of free platinum atoms that are capable for absorption of molecular oxygen. And all of that leads to substantial improvements in catalytic activity. So based on that, we can learn and we can collect design rules for ultimate catalyst, which our hope was to make something like ideal octahedron where only platinum atoms are going to be exposed while nickel is going to be in subsurface, and to get there is extremely challenging. So in order to pursue something which is so-called rational approach, we need to have all of those parameters under control. And as I introduced in the beginning, one of The first of them is actually to make sure that we have very good control of particle size. So how to get there into particle size control, shape control, and compositional profile control, it's really extremely challenging if we are targeting to control all of them. So the first step is certainly to introduce size control, and the method of choice was so-called colloidal solvent thermal approach, which is chemical method of making nanoparticles in such a way that we can be confident to claim they are coming as monodispersed, so very narrow particle size distribution. So just to get you an idea how they look like, so those are not only pure metals, so they can be alloys, and here is a representative example of platinum cobalt particles, which reflects extremely homogeneous distribution of alloying components along with very narrow particle size distribution. So that was exactly what we were targeting. So at the same time, we were controlling both composition and size. So the next step was also to investigate to which extent we can rely on appearance of so-called platinum skin, and that was confirmed by using a number of different annealing protocols, and we found something which was optimal temperature for nanoparticles, which average particle size was around 5 nanometers, so the optimal temperature was between 4 and 500 C. And then the last step was actually to investigate to which extent we can keep adding non-platinum component in order to maintain those desirable properties. And it turned out to be that sweet spot was around 50%, so 50% of platinum, 50% of alloying component. And in reality, that leads to the following. So here is an example of particle which is as synthesized, having platinum and nickel on the surface. But once we expose that to reactive environments such as acidic electrolyte, then whatever is non-platinum component is being dissolved instantaneously. And that leaves a particle with so-called platinum skeleton type of surface, highly corrugated with large number of those under-coordinated atoms, which are not desirable, as we could see from those durability studies. And certainly that was not the last step in our treatment of catalyst. So what we were aiming for is something which is like ideal type of skin. And here our intentional dissolution of surface nickel was leading to skeleton type of surface, and then after annealing we were looking into particles that were much smoother in terms of morphology, but at the same time they kept very desirable surface compositional profile, and the thickness of that layer was at least 2 monolayers. So that was extremely important, not only to achieve high activity, but also to address durability issues. But before I get there, I would like to show you another unique properties of these skin surfaces, which is coming from the fact that actually, as you could learn from one of those slides, hydrogen UPD region is greatly affected. And all of us are using hydrogen UPD as the main parameter to estimate electrochemical surface area. So if we are looking into something which is altered hydrogen UPD region, then consequence of that is that we cannot rely anymore. So in order to resolve that and to address that issue, we are introducing CO stripping as alternative method to estimate electrochemical surface area for platinum-based surfaces. So here we are looking into platinum nickel particles that are actually sensitive to hydrogen UPD, because that was expected for the fact that we are looking into skin surfaces, but also they do not have any effect on CO stripping. So CO stripping is not affected if we are looking into that integrated charge. So we are not talking about the shape of the curve, but we are talking about integrated charge below stripping curve. So in order to use those claims, of course, behind all of that was careful study on single crystals, and then we could switch over to nanoparticles. But the message here is whenever we start to be involved into platinum alloys, we cannot rely anymore only on hydrogen UPD as a single parameter for estimation of electrochemical surface area, because that can ultimately lead to overestimation of our activity. So going back to this multi-layered platinum skin, you can see here summary of electrochemical analysis and also in situ structural analysis by XAIS, and finally summary of activity and durability studies. So not only that those surfaces are extremely active, and this is almost for factor of 10 compared to platinum carbon catalyst, but they exhibit extremely high durability due to that desirable skin, which is probably very close to one-on-one type of surface structure. So in other words, here we were able to achieve both, to address activity and durability. And this is only one strategy in addressing durability. So I will show you a few more examples where durability was successfully addressed. But before going there, I would also like to discuss this type of catalyst with multi-layered platinum skin surfaces from a different perspective. So here still we are looking into solid particles, but more recently we learned how to actually treat our high content nickel catalyst in order to obtain those hollow structures. That was done in collaboration with Pei-Dong Yan from UC Berkeley. So platinum nickel 3 nanoparticles were intentionally exposed to oxygen-rich atmosphere, which induced so-called spontaneous corrosion, which led to those like open frame structure. And ultimately we spent just from going from here to this type of particle with multi-layer skin surfaces, we spent significant amount of time to actually be able to control and to tune surface composition in such a way that actually indeed once we start looking into those like structural characterizations, we could confirm the thickness of the platinum layer was at least 2 atomic layers, and with very high nickel content inside of each frame. So the thickness of each frame was around 2 nanometers, and basically we are looking into something which was like nicely ordered 3D-dimensional network of nanowires, nicely assembled into those nanoframes. And for the first time, actually, one can see actually this type of like third-dimensional accessibility and in other words, extremely high utilization of platinum. So for the first time, there was no buried platinum inside of solid particle, just open frame structure, which allowed, again, extremely high utilization of platinum. Here you can see those short 3D-dimensional movies that are confirming actually this like open frame structure. In addition to ability to tune surface composition and structure in some way for nanoparticles, it has been proposed by Erlebacher and Snyder that one can increase oxygen solubility by introducing so-called ionic liquids into highly porous particles. And those nanoframes were, I would say, probably one of the most extreme examples of those highly porous systems. So in other words, it was ideal system to expose those kind of architectures to ionic liquids, to soak them and to encapsulate them, and then to see how all of that affects activity. And indeed, we could get actually significant boost in both specific and mass activity after introducing ionic liquids, and those are the final numbers that were obtained in rotating disk electrodes. So we are looking into specific activity increase, which was over 20, and extremely high increase in mass activity, which was over 35 when compared to platinum carbon. So Again, all of that was obtained in rotating disk electrode, and certainly our main goal is not only to look systems into rotating disk electrode, which is kind of like ideal environment, but I will get to our final goal, which is how to assemble and how to utilize that in MEA. But before I approach that subject, I would like to show you a few more slides that are reflecting our ability to tackle durability of catalyst at fundamental level. So we all know when we mention durability of platinum carbon catalyst that morphology before and after is substantially altered. So after a number of potential cycles, we are losing electrochemical surface area. We do see agglomeration, and catalyst is losing performance. But this is something which I always like to show. However, this is not how state-of-the-art platinum catalyst looks like. So this is example from our own like monodispersed particles. So what we have in reality is pretty much, it could be confusing, it could be misleading, and I think in many cases this is source of some wrong conclusion actually that we can find in the literature. So first of all, we don't have monodispersed particles in most of the cases. So this is a mixture of many different particle sizes and shapes. And from some unknown reason, to be honest, I don't know why everyone calls them cubo-octahedral type of shape, because they don't have any like regular type of appearance, because they can come as really like a group or cluster of atoms, and all the way to something which is like 50 nanometers in diameter. So we have to be careful actually what is our starting point before we make any claims what is final point. So this is something which I use, and this is something which is, I would say, common case, starting point of state-of-the-art commercial catalyst, and this is something which is obtained after potential cycling. So it's very difficult to make, this is my message to you, so it's very difficult to make any straightforward claims based on those findings. So in order to be able to resolve real effect, we need to look into something which is well defined, at least for the particle size parameter. So for that reason, I'm going back to our initial slide and also awareness that particle size is extremely important parameter, and having something which is monodispersed particles, we can not only address actually what is direction of catalytic performance in terms of activity, but also one can say how durability is affected to the same extent, because they are differently active, but also they do behave very differently in terms of dissolution of platinum, as we could see. So for that reason, it is extremely important to have control of shape effect, because shape effect is bringing us ability to expose certain facets only. So those are examples of like I would say monodispersed cubo-octahedron particles versus truncated cubes versus cubes that were obtained in our labs. So again, in addition to size, here we are introducing shape effect. So and how all of that can be combined and utilized is given here. So again, this is something which is commercial catalyst, and we would really like to get control and awareness of situation at the topmost surface level. So, but in order to get there, it would be impossible without utilization of single crystals. So here is one-on-one why inclusion of single crystals is always necessary. And again, I'm bringing this slide because in recent times we can hear, especially from industry side, we can hear that actually studies on rotating disk electrodes are not relevant for the real world catalyst. And this is absolutely wrong message, and this is absolutely something that everyone should be aware that this is not the way to go. So single crystals should be always in focus, because that's the only way how we can learn and how we can transfer knowledge from fundamental to something which is applied. So, and here one can see one-on-one actually ideal 100 type of surface and voltammogram with compared to cube particles, and actually voltammogram which resembles 100 type of surface. So in other words, knowledge is translational, as we could see not only from this example which is on the current slide, but also from those platinum alloy particles. I will just go quickly over this slide because it depicts actually ability to achieve this high sensitivity which I already mentioned. So we are introducing whatever is coming from electrochemical cell. We are introducing electrolyte directly into plasma source, which is which comes with a temperature which is approximately 10,000 degrees, and then everything is being atomized and ionized, of course, and those ions are coming into mass detector. And as I said, we are looking into something which is pretty much PPT, part per trillion level sensitivity. So this is only a reminder what I already said. So fact that we could achieve extremely high sensitivity and also structural dependence of platinum dissolution. So right now we have absolutely detailed insight into structure function properties, which means activity and durability for single crystals. And here's just like a summary of how one can utilize and quantify different type of analysis. And I always like to bring up actually fact that it's always extremely important to be aware of detection limit, and this is something that we are carefully doing for any kind of new analysis. So we are just not throwing those numbers here. So there is a huge know-how before we put any number into a place. So and again, the message here is actually platinum dissolves, and the main challenge is what and whether something can be done. So what is the best way to mimic morphology of nanoparticles? So in addition to ability to control size, we can also we cannot do too much to control active electrochemical surface area, because sometimes those particles detach, and the most ideal case is actually to work with extended surfaces. And we already showed in past the best way to do that would be to employ thin films. And here you're looking one-on-one behavior of platinum carbon state-of-the-art catalyst with thin film, which was obtained by sputtering. And they behave pretty much the same. So the same type of dissolution, which is not surprising considering morphology of those thin films, highly corrugated with average cluster size of being between few and 5 nanometers, exactly as in case of state-of-the-art platinum carbon catalyst. So I would say comparison is 1-to-1 in terms of dissolution and behavior from each potential cycle, depending on upper potential limit. And here is case when we use the same film thickness of platinum, 4 monolayers, but what is different, we put several monolayers of gold in subsurface. So in other words, message to take home here, we can indeed influence to high level. We can completely diminish the dissolution of platinum by introducing gold in the system. Of course, gold is not the most desirable element to put because it brings additional cost. However, here we are looking into few atomic layers of gold and platinum that are positioned in very distinct way, and by doing so we can completely diminish and get rid of platinum dissolution. So again, this is extremely important design rule, so which was immediately applied to several of those so-called core interlayer shell type of particles, and due to extremely high onset of formation of surface oxides, gold is much less oxophilic than platinum, as one can see from those voltammograms on this slide. Gold in background versus platinum type of surfaces. So, and here is how our core shell particle looks like. Gold in subsurface coated with at least 5 platinum-based type of shell. So not only that we are using that knowledge of mixing gold with platinum in a very controlled way, but also we are introducing alloying components such as cobalt and nickel in this shell. And more recently, as I said, it's not only gold shell, but actually it is gold interlayer with nickel core. So in order to make all of that more cost effective, so we used like cheaper material such as nickel, and then we coat it with gold, and then we end up with several monolayers of platinum nickel shell. So what that brings is the following. Those are like typical platinum carbon catalysts before and after, and also platinum nickel commercially available before and after. And this is something which is our core interlayer shell, so absolutely no change in surface morphology, no change in performance. So indeed, placing gold in such a way can address durability issue very effectively. So that was one way how one can improve not only activity but durability as well. So the other was, as I mentioned, was that multi-layered platinum skin. And now I would like to show you a few examples of how those advanced catalysts are behaving in MEAs. So MEA is different environment than RDE. Rotating disk electrode is again, ideal electrochemical environment without any impurities. And MEA, we are looking into surface chemistry, which is much more complex. Plus, we are introducing ionomers. So this is summary of MEA studies, which was done here at Argonne in collaboration with Debbie Myers. And we employed our platinum nickel nanoframes with multi-layered platinum skin surfaces, and mass activity was improved for 3.5 and specific activity for 6.5. So our main limitation here was the amount of material that we are able to produce. So for that reason, we recently launched a new effort here, which is focused entirely on scale-up of those materials that are extremely active and they have advanced properties. So we are hoping in the near future that we will produce much higher amounts of materials, and that is going to allow us to spend much more time in optimizing and to find ideal conditions that ultimately and hopefully will lead to numbers that can be compared to the numbers that we are obtaining in rotating disk electrode. Also, here is a snapshot of how those advanced catalysts such as nanoframe, how they look like before and after MEA treatment. So they do preserve shape, and they do preserve also compositional profile, having that platinum skin on the surface. Another example is also in addition to nanoframes, and actually we like, and our intention was to start with scale-up effort with those like simpler systems such as solid platinum nickel nanoparticles with multi-layered skin, and we already obtained results that are currently matching whatever numbers were obtained from nanoframes just for one-shot experiment, and right now we are in position to produce really like gram amounts from a single batch, and we are already collaborating with stakeholders and then and other national labs actually on optimization of MEAs. So that would be the latest development from our labs. But in addition to those like advanced systems that are making in our labs, I would also like to mention a couple of them that are a notable example from literature. This is a recent report from a research group that is coming from UCLA. So they were able to produce platinum nickel octahedrons, and they also introduced moly as ingredient like ternary alloy, and they do claim that introduction of moly substantially improved activity, and they were able to reach pretty high values and high numbers for both specific and mass activity. And again here we're looking into those numbers that were obtained in RD, not MEA. Another interesting example is also some type of nanowires, but you do see those like zigzag type of shape. So in other words, they are utilizing in some way advantage of having extended surfaces and also flat surface morphology, but they are at the same time increasing electrochemical surface area by introduction of that zigzag type of structure. So again, very high performance in terms of activity and durability as well, so before and after cycling. This is research from report from a research group in China. So this is work from Peter Strasser, and actually he is known for careful observation of de-alloying, and of course once you have atomic species that are not platinum as initial point, they always serve as, I would say, active sites for dissolution or de-alloying, if you like, and that leads to different type of morphologies. And I would say the biggest challenge here is actually to which extent they're stable. So because I mean in each of those cases we are looking into some kind of like skeleton type of surfaces. So another notable example is work from Denmark, and they're using rare earth elements in order to boost catalytic activity, but at this point they were mainly looking into extended surfaces because it's very challenging to make those materials in form of nanoparticles, but very important work and valuable observation reports from this group. So it's also important to mention several of those like studies that are focused. This is Yu Shan-Yang from Delaware, and in collaboration with Brian Pure from NREL. So platinum copper nanowires, in fact, that they can control the alloying to the extent where actually system becomes stable. So, and also very well known from Brookhaven lab, so-called platinum monolayer approach, where they carefully coat by galvanic displacement. They coat so-called platinum monolayer, but that shouldn't be confused with single atomic layer. So this is just like platinum shell type of coating on different kind of materials. And I would say the most famous example is palladium coated with platinum shell. So I'm approaching the end, and I would like to say a few words about remaining challenges and barriers. This is certainly durability, cost, and performance, but you should also be aware that there are ways how we can address them successfully, and I think whatever I showed, it's very convincing in terms of potential that fundamental approach can offer. And for that reason, it is really important to stay focused between RD and MEA, and to be aware of differences and similarities between those two environments. Another parameters that are not greatly discussed are temperature, and also fact that high current density region in MEA is another topic which needs to be addressed while we are trying to decrease the total loading of platinum. So those two do not go together. So extremely low loading and high current density regions, so usually they collide. And I would also emphasize support, because in most of the cases we take for granted that support is carbon-based. But what type of carbon? To which extent we can alter carbon in order to improve both stability and durability, activity and durability, and certainly scale-up process for all of those advanced systems. So this is just another example of how single crystals can be utilized in elucidating those important properties in MEA interfaces. So single crystals with ionomer and how they alter adsorption properties. I think this is extremely valuable approach. So those are results that were done in our group. Another example which follows directly from that is what can be done if we do see strongly adsorbing species like here. So ionomer is potentially something which should be considered strongly adsorbing anion, and here is an example either with sulfates or phosphates what they are doing for catalysis of oxygen reduction reaction. Substantially inhibited. However, if we put cyanides, they can diminish that negative effect, and surface which is pre-covered with cyanides can actually reverse activity in both sulfuric and perchloric acid to activity level, which is usually obtained in perchloric non-adsorbing electrolyte. So I would say extremely good example how one can potentially look and design interface in order to diminish negative effect of ionomers. A couple of examples that I obtained from our colleague in Oak Ridge, from Karen Moore, like different type of carbon supports, and that would be what we have right now, and something which deflects necessity and topic and opens the topic, like to which extent all of those catalysts are functional inside of MEA, versus case where we have something which is so-called like highly ordered faceted graphitic shell. However, all of those particles that are functional for catalysis, they're sitting on the shell, so in other words, they're more accessible for reactive species. This is another example of capabilities for imaging from Oak Ridge, that basically three-dimensional awareness of where are catalyst particles versus carbon support. And in addition to that, it's also important to be aware of ionomer structure, and they can now efficiently model three-dimensional structure of ionomer by making all of those slices, and one can be aware of the exact pore size, of the exact position of ionomer, and in other words, we can get almost three-dimensional real-time structure of electrode in MEA. So here I would like to close and to emphasize activities in our labs, and I think that should go across the entire field. So starting from fundamentals and doing work which is focused on a number of those like advanced catalyst systems, and we are considering now both, not only particles itself with controlled shape and compositional profile, but also advanced catalyst supports. And we are bringing immediately all of those promising systems into our scale-up lab, and we are producing those MEAs which are not only tested here in our lab and not only among our network of collaborators, but they should be, and they are already available to OEMs and whoever might be interested in getting those advanced systems. So, and I would like to end with something which is a message to take home. Regardless of those like different type of catalyst, and they can be solid nanoparticles with different type of surfaces, core shell shaped or nanoframes, in order to get there and to claim what is behind advanced behavior, we need to use single crystals, and the only way to do that is always to rely on RD and on connection between RD and MEA in order to get something where Toyota is already proved that actually connection between fundamental knowledge and applied is feasible. So before I end, I would like to mention people who are part of research effort here at Argonne. Myself and Markovic are PIs of fuel cell project, and we have several full-time postdocs, Dongguo Li, Haifeng, and Rongyue Wang, who is making scale-up synthesis, and certainly we are supported with a number of colleagues, not only from Argonne, but also collaborators from university and other national labs. So it is also important to mention people who are not currently in the group, but they substantially contributed to accumulation of knowledge that is not only at fundamental but highly applied level. And currently those people are scattered among universities and industry, and we still stay in touch. And also would like to mention our colleagues here from Argonne, Debbie, who is helping us with MEA, and Peidong with his synthesis effort, and certainly Karen Moore, who is providing that structural insight. And the most important is, of course, funding, which is coming from ERE office, FCTO, who's been supporting our fuel cell effort for a number of years, and I think that has been very fruitful two-way collaboration. So our single crystal work is usually supported by Office of Science, Basic Energy Sciences, but you shouldn't be surprised to say that in some cases actually we do get substantial support to do single crystalline work, and that support is coming directly from industry, and it is, for that reason, it is important to stay aware that fundamental knowledge is the only way how we can advance the field. So let me thank you once more for participation, and that would be the last slide that I'm showing, and I will be happy to answer questions.
Thank you, Voya. We have about 5 minutes or so, and I have a couple of questions for you, at least, that we can, I hope you can answer in that time frame. So the first one is, I think just a clarification question. The nanoframe catalyst consists mainly of platinum, am I correct?
Nanoframe catalysts are platinum and nickel.
Okay. So the first question that I have then is, there seems to be considerable focus on platinum nickel at Argonne. Has the presenter considered other transition metals, such as cobalt?
Well, actually, this is how we started. We started from cobalt, and somehow we diverged into platinum nickel for a very simple reason, because nickel is easier to use in synthesis methods, so it doesn't produce too much issues of with interaction with membrane. So cobalt would be equally good, but cobalt is very challenging for synthesis because sometimes precursor of cobalt is considered to be carcinogenic. So for some safety issues and concerns, we are always careful to use cobalt in our synthesis lab. However, we do have, and unfortunately we didn't publish yet, a number of studies that are related to platinum cobalt single crystalline surfaces, and I hope we will have that out very soon. So, and in fact they're very similar to each other, so there is nothing like there is nothing too surprising out of that. So those two are equally important and equally good, I would say.
Okay, thank you. Another clarification question that came in is the following. In MEA, were the mass activities measured from hydrogen-oxygen data or hydrogen-air data?
So those data and numbers that I pointed out, that was from hydrogen-oxygen. So, and we do have data for hydrogen-air. Of course, that drops even lower in terms of numbers that we are looking at, but what I presented was hydrogen-oxygen.
Have you looked at the activity and durability of the novel catalyst structures at higher temperatures, let's say 150 to 300 Celsius?
That high was not considered, but we definitely consider temperature range which is relevant for MEAs, so going up to 80 C. This is something that we usually do, but 150 and 300, no, except actually looking into so-called like thermostability, whether this, let's say, frame structure is going to collapse, whether frame structure is going to survive after exposure to 300 degrees, and basically we confirmed it can survive up to 350 or so.
Okay, thank you. This is a platinum dissolution question. So the question is, where does the platinum go after it dissolves? Is it retained by the membrane or does it pass through?
That's an excellent point. So, and first of all, when I was talking about platinum dissolution, that was done in RDE. So basically that platinum goes into electrolyte, and then that electrolyte is being sucked up by our specially designed RDE probe. So what is going on in case of MEA, of course, it migrates toward membrane, and this is why it's not surprising that in many of those studies we could see accumulation of platinum next to the membrane, and sometimes even penetrates through the membrane.
So I assume there are ways to reclaim it then, or replace it?
Yes.
Okay. So I think in the interest of time, I have one last question that I think is pretty interesting. Do you think non-precious metal catalysts will finally replace those precious metal catalysts?
I would say this is ultimate challenge, and this is far future that all of us would like to believe this is going to happen. But before addressing that, it's really important that we stay with something which is already in place, and it can be applied in real systems. It can be applied in Toyota Mirai. But the ultimate goal, it remains to be seen. This is why we are still all around, and hopefully we can get answer to that over the next few. I would say it's too it's premature to say like over the next few years, but over the next few decades, hopefully. But I think in the meantime we need to make sure that we are making the best what we can out of those precious metal-based catalysts, and at the same time to work in parallel with non-PGM or PGM-free systems.
Okay, Voya. Thank you very much. I'll hand it over to Chris.
Thank you. Voya, if you want to go back to that last slide there and throw that up for me, that'd be appreciated. Thank you, Dimitrios, for hosting the webinar. Thank you, Voya, for this top-notch presentation. I certainly enjoyed the beautiful graphics that accompanied your information. Thank you as well to the audience. I'd like to remind everyone this webinar recording and slides will be posted to our hydrogen and fuel cell website. That's hydrogenandfuelcells.energy.gov in about 10 days. We will send out an email to all attendees once those are posted. You can also sign up for our newsletter at this website, which includes registration for upcoming webinars, as well as information and opportunities relevant to the hydrogen and fuel cell community. Thanks again, everyone. Have a great rest of your week. Goodbye.
Thank you.